Hi everyone, today we're going to talk about absolute entropy and entropy change. So a word you may have heard me use previously before in the class is spontaneous. Now, spontaneous in chemistry doesn't mean, crazy or random or anything like that. All it means is that a reaction proceeds without an outside force. So this example here, H2 plus Cl2, if I mix those two together in a container, it's going to make 2 moles of HCl no matter what. I don't have to put any outside force in order to do that. Therefore, a non-spontaneous reaction means an outside force is required for a reaction to happen. So I need to put in some sort of extra energy to make a non-spontaneous reaction actually happen. Now, I want to make a clarification here. Spontaneous does not mean fast. A spontaneous reaction can take years, it can take hours, it can take days, it can take seconds. It doesn't mean fast, it just means that you don't need to put any force into it for it to happen. And non-spontaneous doesn't mean that it will never happen, it just means that you need to put in the right amount of force for it to happen. And so there's some factors that can affect spontaneity. Temperature and pressure can. For example, here, this is an example of how temperature affects ice melting or freezing, right? For T greater than 0, or above freezing, right? If the temperature is above freezing, it melts spontaneously, right? If I have a block of ice and I put it into a room that's at room temperature, it's going to spontaneously melt because I don't need to put any extra force into it. It's just sitting there at the temperature and melting. But at less than 0, it's in the opposite direction. And so if I have a block of ice at negative 20 degrees Celsius, right, it's going to freeze spontaneously. It's just going to stay like that. It's not going to melt because you need to be above a certain temperature. And so it's spontaneous in the opposite direction. And so all of this relates back to entropy. Entropy is what we call a state function. We've talked about this before, but it means it's independent of the path a reaction takes. In other words, all that matters is where you start and where you end. And you can calculate the change in entropy, similar to the change in enthalpy, by doing S final minus S initial. So the entropy at the start minus the entropy at the end. And it can actually be found from heat. It's basically the heat transfer from the surroundings at a given temperature. And so you can calculate the change in entropy. You will never actually be given entropy in initial and final state. Instead, you can find the change in entropy by looking at the Q, what we call Q rev, over T, where Q rev just means the heat transfer in a reversible process. And T is, of course, temperature. And so we can find entropy given these two parameters. Now that also brings me to the second law of thermodynamics. I said in the last video that we weren't going to talk about this quite yet, but the second law of thermodynamics relates heavily to entropy. This basically says that the entropy of the universe increases in any spontaneous process. So if I have a process spontaneous, it occurs without any outside force, the entropy of the universe should always increase. And so this basically leads to the following two relationships. For a process that is at equilibrium, the change in entropy of the universe is equal to delta S of the system plus delta S of the surroundings And since it's at equilibrium, this will always equal 0. If you add the entropy of the system and the entropy of the surroundings, those two will equal the entropy of the universe, and that is always going to be equals to 0 if you're at equilibrium. For a spontaneous process, this must be true. Delta S of the universe, which is defined as the entropy of the system plus the entropy of the surroundings, is always going to be greater than 0. In other words, what this says is that the entropy of the universe always increases or stays the same. If you add up the entropy of the system and the surroundings for any system and surrounding that you're observing, it should always be at 0 for equilibrium, for a process at equilibrium, or it's going to be greater than 0. It should never be negative. Now, because entropy is a state function just like enthalpy, a change in S, or a change in delta S of a reaction, can be calculated the same way as delta H of a reaction, because delta H, or enthalpy, is also a state function. And that is that delta S naught of a reaction is equal to the sum of delta S of the products minus the sum of delta S of the reactants. Right, and so whatever the entropy of your products are minus the entropy of your reactants, that gives you the entropy of the entire reaction. And remember, stoichiometry still applies. So you have to multiply any of the products or reactants by their stoichiometry and equation. Just like with enthalpy, we have tables of standard entropies. They increase with molar mass, and so as molecular weight goes up, delta S also will go up. And it increases with the number of atoms in a formula, right? And so more atoms equals higher delta S. And you can see that here. H2 is 100, its S value is at 130. But if we look at H2O, for example, right, that has 3 molecules in it, that's at 188. If you look at C6H6, that's a lot more molecules, it's at 269. And so as you increase the number of atoms in a formula and increase the molar mass, your standard entropies, or S naught, will go up. So let's look at this one example here. We're given this equation, 2SO2 plus O2 makes 2SO3, and we're told that delta S of the reaction, right, because we're in moles of reaction, so delta S naught of the reaction is equal to negative 187 joules per mole degree Kelvin, or joules per mole Kelvin. So the reaction between SO2 and O2 is represented by the chemical equation above. The table provides the approximate values of standard entropies, and so here we have S naught for all of our species, and we're interested in what is S naught of SO2. Well, we know that delta S of the reaction is just equal to the sum of S naught of products minus the sum S naught of reactants. So delta S of the reaction is negative 187. We know the entropies of our products for oxygen, and I'm going to do this in brackets. It's 205. And then we have 2 SO3, right? And so we have to do 2 times 257. And then we subtract from that the entropy of the reactants, which will be 2 times the entropy of SO2. And that is what we were trying to find right here. And so if you rearrange this equation, what you find is that S naught for SO2 is equal to 1/2 187 plus 2 times 257 minus 205. So our answer choice there is C. In this case, we didn't actually have to calculate it. All we needed to do was rearrange the equation to show that. But this works pretty much exactly the same as enthalpy. And so when we are doing those enthalpy calculations, these standard enthalpies of formation, this works exactly the same way. We'll talk about this a little more in class, but for now, that's all. Thanks, guys.